In this video, you'll be learning everything there is to know about load combinations. So if you have ever done structural engineering and design using any of the softwares, you must know the pain of not knowing about what kind of combinations to take using the primary loads like dead loads, live loads, wind loads, and seismic loads, like how to combine them and when to combine them and for which members to combine them. So if you have had any doubts with respect to load combinations, I'm sure this video is going to clear them out for you. So without any further ado, let's jump into the topic. Hello and welcome to Civil Black Box. This is the channel where we talk about civil engineering concepts and more particularly about structural engineering concepts. So if you're interested in either of those, please do consider subscribing to this channel. Also, while going through this video, if you do find value out of it, please do not forget to hit that like button. It really helps with the motivation as well as the YouTube algorithm in general. Finally, I do have a free ebook for you to download, which will show you the 12-step process of creating your own structural consultancy business. If you are interested in that, check it out. The link to the free ebook is going to be down in the description below. Without wasting any more time, let's jump into the topic. So let's try and understand this load combination concept. Now, when we're talking about the load combinations, we'll be looking at this from three different angles. We'll be looking at it from the concept of what are going to be the load types. We'll also be understanding what are going to be the member types. And finally, we'll be understanding what are going to be the load combinations type. Now, we are looking at it from these three different perspectives because the combination types is linked with either of these. So we cannot just look at the combination types in isolation because each combination type is particular to a member type and each member type is particular to considering what load types are there. Do not worry, we'll try and break down each and every concept. Let's start off with the load types. Now, when it comes to load types, we usually work with four different load criteria. We have the dead load, which comes from the IS 875 part 1. Again, I'm mentioning the Indian standard code. If you have an equivalent international code like American code or British code, please hit me up in the comments. I would love to know the comparison between the two. Also, it will kind of give me some idea of creating a comparative video on that line as well. Next up, we have the dead loads, which comes from the IS 875 part 2, which talks about imposed loads. So imposed loads and live loads, I'll be using the term interchangeably. Next up is the seismic loads, which comes from IS 1893 part 1, which is the criteria for earthquake resistant design of structures. Finally, we have the wind load, which comes from again IS 875, but the part 3 of it. These are the four different primary load criteria which we have to understand. Now, I won't be going into the detail of how to calculate them, but you have to understand that these are the four criteria which will be used in the load combinations. Now, for the dead load comes from the self-weight of the structure itself. So every member which you are modeling in your staad or whichever software. So if you are, say, modeling the beams and the columns and the foundations, that will become the part of the self-weight of the structure. If you are defining the slab load as a floor load, that will become the part of the dead load. So everything which is going to be a part of the structure will be taken as a dead load. For example, wall loads. So different wall types will give you different wall loads. We have criteria like ceiling plaster, tank loads, etc., etc. So everything which is going to be available as a part of the structure, which is not going to move, will be the dead load. For the live load basically depends upon the type of room which we are taking into consideration. So for example, if you are talking about, say, living rooms or suites, the criteria for live loads is a bit different. For the corridor areas, the live load concepts are different. For the kitchen, for the toilet, for the roof, etc. So live load basically depends upon the criteria of the area into consideration. Next up, we have the seismic load. Now, seismic load comes in different flavors. We primarily work with static and dynamic. I have already made a video on static loads where I go into very much detail. Do check it out in the description. I'll put a card somewhere here as well. Next up, we have the dynamic load criteria. Now, we usually work with dynamic load criteria just because of the fact that most of the places inside the country are in a severe seismic zone. And for the severe seismic zones and for a multi-story or a multi-level building, we usually work with dynamic load. So in essence, we are talking here about the dynamic load as a primary load criteria. And we are talking about them with respect to the natural torsion and the accidental torsion into consideration. I'm showing natural torsion and accidental torsion not to scare you away, but just because of the fact that natural torsion and accidental torsion become a part of the primary load criteria. And we'll have a look at it in a few seconds. Lastly, we have the wind load criteria, where we, in essence, talk about the wind load application on the windward phase, the leeward phase, the sidewall phase, and so on. Moving on, we have one special criteria which comes for the live loads, which is a concept called reduced live loads. Now, this is particular for columns and foundations only. I'll take you inside IS 875 Part 2 Clause 3.2, which clearly mentions that while designing columns as well as foundations, the following reductions in the assumed total imposed loads can be made. So we can reduce the live loads with respect to the criteria given here. I'm not going into too much detail about it, but in a sense, we can reduce our live loads when we are designing columns and foundations. Now, if you do want to understand more about how this load reduction is done for the live load criteria, do hit me up in the comments below and I'll try and make a video on it. All in all, when it comes to columns and foundation, we'll not be working with full live loads, but rather with a reduced live load concept. So that is all about the live loads, or rather a quirk about live load. Next up, one more important thing, which I'm not going to be mentioning in this video, but you should be understanding that when it comes to seismic loads, we usually work with horizontal directions of seismic loads. That is the earthquake load in the X direction as well as the earthquake load in the Z direction, considering both of these are the horizontal direction. And we do not work with earthquake in the Y direction or the vertical direction. We, however, need to work with the Y direction when it comes to irregular or complex structures. Since we usually work with regular structures, we do not go into it. But once we are working with irregular or complex structure, we have to understand that the load combinations criteria changes a little bit. So rather than now working with just the EQX or the EQZ, we now have to work with earthquake X plus minus 30% of earthquake in the other direction. That is, say, if we are working with X, then Z plus minus 30% of earthquake in the Y. So that is what this criteria is talking about. Usual cases, we just work with this plus minus earthquake L and plus minus earthquake Z. However, if we are working with an irregular complex, we take 30% of the seismic load component in the other two axes as well. Again, the load combinations which I'm going to be showing you will be for a simple regular structure and not for an irregular or complex structure. So keep that into mind. I just wanted to show you what the additional complexity is for a complex structure. So these are everything about dead load, live load, seismic and wind. Let's understand what are going to be your load containers. So for the dead load, we just have a single criteria which will encapsulate all the different loads under it. Then we have the live load criteria. Again, this will encapsulate all the live loads. So for the room, for the corridor, etc., all of this will come inside live load. When it comes to seismic load, however, we have different criteria. For seismic load, we'll be defining our earthquake load as something like this. So earthquake in the X with a factor of 1.5. I'll talk about it in a bit. We will define earthquake X with a factor of 1, earthquake Z with a factor of 1.5, and earthquake Z with a factor of 1. Now, when we are talking about this 1.5 and 1, we are essentially talking about the concept of natural torsion and accidental torsion. And that is why I had to mention it previously. When it comes to dynamic loads or static loads for that matter, we have to understand the natural torsion concept and the accidental torsion concept as well. So when we are denominating this factor as 1.5, we are actually talking about this entire load case criteria where we have the static eccentricity as with a factor of 1.5 and the accidental torsion with a factor of 5%. When we are talking about this 1, we are essentially talking about static eccentricity being with a factor of 1 and the accidental torsion being with a factor of minus 5% of BI value. Again, I'm not going into the details of what this ESI and BI is, but you have to understand that when defining seismic loads, this is not going to be a single criteria like the live load, but it will be broken down into 4 different concepts. The same goes for wind load as well. Instead of having just the wind load, we have wind load in the plus X, wind load in the minus X, wind load in the plus Z, and wind load in the minus Z directions. All in all, the primary criteria will be 10 in number. So 1 for the dead, 1 for the live, 4 for the seismic, and 4 for the wind loads. And all the combinations will be a permutation of all of these. So this is everything about load types. Let's talk about member types as well. So when we are understanding member types, there are basically 4 types of members which we kind of design in any of the softwares. We design beams, we design slabs, we design columns. Now, when it comes to columns, we have seen that the live load reduction has to be done. So that will come under the criteria of reduced live load. We also have to design foundations, again, which comes with a criteria of reduced live load attached to it. The beams, columns, and slab usually form a part of the superstructure, and the foundations form the part of the substructure. So we'll be kind of defining beams, columns, and slabs as a superstructure part and substructure being foundation. So this is everything about member types. Finally, we have the combination types. Now, when it comes to combination types, we have usually seen, or you might have also usually seen, that we have two criteria to look for. We have the ultimate strength criteria and we have the serviceability criteria. So one is the limit state of collapse and one is the limit state of serviceability. Now, these two come from IS 456, which is for plain and reinforced concrete code of practice. Again, everything which I'm talking about is with respect to RCC structures only. Now, this is not the end of the story. However, there is one more criteria which is kind of overlooked most of the time, which is for the proportioning of foundation. Now, this comes from IS 1904 and will again go into very much detail about what each of these criteria talks about. However, all in all, when it comes to ultimate strength and serviceability, this is the code snippet from IS 456 table 80, which says that for the superstructure, we'll be taking the criteria as such and such. And for the foundations shall be analyzed and designed for. That is, for the ultimate strength part, we'll be taking the criteria as per IS 1904, which kind of boils it back to this criteria itself. So this is basically saying that the foundation shall be analyzed and designed for all the combinations used for superstructure analysis. So everything that we are doing for the superstructure analysis for the ultimate strength part, we'll also be doing it for the foundation. So all in all, that boils down to the concept that ultimate strength or the limit state of collapse is the same for the superstructure as well as the substructure. Next up, we have the criteria for proportioning. For the proportioning, this is a bit different because this is again often overlooked. As per IS 1904, this is saying that the foundations shall be proportioned for a different set of load combinations. So this is not talking about going back to what we are doing in superstructure, but this is giving its own criteria. Again, we'll be going through very much detail of what these values are. All in all, for the ultimate combination types, we are working not only with the superstructure, but the substructure as well. And this comes from IS 456. For the serviceability part, we are just working with superstructure. And for the proportioning part, we are working with the substructure. This comes from IS 1904. Again, do not worry, I'll be going through each of them one by one. Finally, when it comes to the ultimate combinations types or the strength combination types or the design combinations type or whatever you may want to call this first factor of combination, this usually talks about the strength of the building with respect to flexure, with respect to compression, with respect to shear, and with respect to torsion. So when we are designing our structure for failure against torsion, shear, compression, and flexure, we are actually talking about the combinations which are given under this ultimate combination type criteria. When we are talking about serviceability, we are actually talking about the criteria of deflection as well as cracking. Now, this criteria is a bit different. For the serviceability, our load combinations have a smaller factor, and for the ultimate, you can understand that we have a greater factor, because right here, we are trying to understand the limits of failure of our structure. Right here, we are trying to understand the limits of serviceability or life of the structure. So during the normal course of your structure, you want to have deflections under check and you want to have cracking under check. However, for the extreme cases, you want to check that your structure does not fail in flexure, it does not fail in compression, it does not fail in shear, and it does not fail in torsion. Thereby, all the factors in ultimate strength will be somewhat around 1.5, and for the serviceability, or rather 1.2 as well. For the serviceability, it will be around 1 and 0.8. So you can understand that the factors are hugely different just because of the fact that both of these are trying to understand or bring out different factors of the structure. Last but not the least, we have the proportioning part. Again, this is different for just the substructure or the footings. So when we are proportioning our footings, that is when we are defining the area of our footings, this is where the proportioning concept comes into play. So this is everything about combination types. Now we are not done yet, because we have understood what are the different load types, we have understood what are the different member types, and we have also understood what are the different combination types. Let's now bring all these together, and we'll be bringing them together with respect to the member types and the combination type. We'll first start off with the ultimate strength, and we have seen that the ultimate strength comes for all the four parts. That is, it comes for not only the superstructure, that is this part, but also for the substructure. So for the ultimate, we are talking about all these four different member types. So let's look at what this criteria of combination is. So we'll take this all together and we'll try to define it. Now, the criteria for limit state of collapse or ultimate combinations comes from IS 456 table 18, which talks about the values of partial safety factor for loads. Now, before I jump into what each of this is, I just wanted to point out one small issue with the code itself, which has been, of course, modified, which is for this 1.0 factor. So if I just zoom into it, you'll be able to see that just for the dead load and live load criteria, so IL basically means imposed loads, which again is interchangeably used for live load. You can see right here we have been given a factor of wind load as 1.0. So this was a typographical error in the code itself, which has been amended. So you can go through the amendment number 1 to IS 456, which clearly says that on page 68 and table 18, column number 4, so this is the column number 4 as you can see, you have to substitute this against this. So 1.0 has now been substituted as a dash. So wherever you are seeing this 1.0, you can just cut it out and understand that this is only considering the factor of 1.5. So I just wanted to point it out so that you do not have any confusions regarding that. So let's go through the limit state of collapse or the ultimate strength criteria in a bit more detail. We'll start off with the first case, that is the dead load plus live load. And you can see we are working with just the dead load plus live load with a factor of 1.5. Again, this factor is not to be considered, so you can just take it away from your mind for now. We'll start off with the first case, which is simply dead plus live. It has a factor of 1.5, so we are ultimately working with the dead load with a factor of 1.5 plus live load with a factor of 1.5. This gives us one load combination with respect to dead and live. Moving ahead, we have the dead plus wind load criteria. So you can see we have rather two criteria here. You can see we have 1.5 or 0.9. So for the dead plus wind, we start off with 1.5 for the dead and 1.5 for the wind. So you can see 1.5 for the dead and 1.5 for the wind. However, you have seen that wind load is not a single component. We have four different cases. So we have wind load in the -x, wind load in the +z, wind load in the -z. So we have four different criteria. Additionally, these four criteria come with a plus sign, but when it comes to wind load, we are working with plus minus both. So we'll be having the same four cases, but with a negative sign. So we get 8 cases in total. Apart from these 8 cases, we have this 0.9 case as well. So everything with a 1.5 can now be replaced with 0.9. So all these factors can now be replaced with 0.9 and we'll get 8 more cases. So I'll just have you go through it. So again, for the dead and wind, we have these cases exactly the same, except the fact that the dead load factor has been modified from 1.5 to 0.9. So 8 more cases there. Now we have one more case, or rather a few more cases for the dead and seismic. So if you go through the notes, you can see that while considering the earthquake effects, you can simply replace the wind load with the EL, which stands for earthquake load. So everything will remain the same right here, except the fact that we are now talking about earthquake load instead of wind load. So the criteria remains the same. We have 1.5 dead load plus 1.5 earthquake load. Again, earthquake load comes in different flavors, or rather different packages. So we have earthquake X with a factor of 1. Again, this was for natural torsion and accidental torsion. So we have 4 cases, earthquake X with a factor of 1.5, earthquake X with a factor of 1 for the static eccentricity, same for Z with a 1.5 and 1. So these are the 4 cases. Again, this is with a plus sign. We can go through it with a negative sign as well. So this gives us 8 cases. Again, we can replace this 1.5 with 0.9. So all these 1.5 will get replaced and we'll get the same cases again, but with a factor of 0.9. Everything on the right side remains the same. So 8 more cases right here. Moving ahead, we have the bottom case, which stands for dead load plus live load plus wind load. So if we go through it, you can see we have the dead plus live plus wind. Again, this one is with a factor of 1.2. So we have a factor of 1.2 dead load plus 1.2 live load plus 1.2 wind load. Again, wind load comes with 4 different criteria. So we have wind load for 4, and again, we have a negative sign instead of a positive sign. So these are 8 more cases for the dead, live, and wind case. The same goes for dead plus live plus seismic. You can just replace the wind load with seismic. We get 1.2 dead load plus 1.2 live load plus 1.2 earthquake X. Again, we have 4 cases for earthquakes, so we get 4 cases. Next up, we have all the cases with a negative sign as well. So we get 8 more cases. All in all, we get the combination types as follows. For the ultimate strength case, that is dead plus live, we have 1 case. Dead plus wind, we have 8 plus 8, 16 cases. This one was with a factor of 1.5 and this one was for 0.9. Again, for the dead plus seismic, we have 2 cases with a factor of 1.5 and with a factor of 0.9. So we are essentially talking about this factor right here, 1.5 and 0.9. So these are with respect to these 2 different factors. Finally, we have the dead load plus wind, dead load plus live load plus wind, and dead plus live plus seismic. So all in all, we get a minimum of 49 cases. So if you are working with additional load cases internally, this figure will increase. But at the least, we should be getting at least 49 load cases. So this is all about the strength ultimate strength criteria. Let's now move on to the serviceability. Now we have seen that for serviceability, we are just working with the superstructure. So you can see we are now just working with the superstructure and the foundation is now removed from here. So we, in essence, we will be talking about just this factor. Let's bring them together and understand what the load combinations are. So taking them together, again, we'll be referring back to table 18 of IS 456, but we'll be limiting our criteria with respect to this limit state of serviceability only. So let's remove everything else and talk about limit state of serviceability. So let's bring that together and let's look at them one by one. So the first criteria is dead plus live with a factor of 1 and 1. Very simple, dead plus live, 1.0 dead load plus 1.0 live load. This gives us one case. Next up, we have the dead plus wind load criteria. You can see we have a factor of 1.0 and 1.0. So 1.0 dead load plus 1.0 wind load. Again, wind load has 4 different cases, so 4 cases. And then we have a negative sign, so 4 more cases. That gives us 8 cases for dead plus wind. Now the same will be repeated, just will be replacing wind load with seismic load. So this now becomes dead plus seismic. 4 cases with a factor of 1 and 1. So you can see with a factor of 1 and 1 right here. Again, 4 cases with a negative sign. This gives us 8 more cases. Moving down, we have the dead plus wind, dead plus live plus wind. So the dead plus live plus wind consists of 1 factor for dead, 0.8 factor for live, and 0.8 factor for wind. Again, we have 4 cases for wind. So we'll get 4 more cases, or rather 4 total cases. Additionally, we'll get 4 more cases with a negative sign as well. So you can see we have a negative sign here. So 8 cases in total. Now the same thing will be repeated, just we'll be replacing wind with seismic load cases. So this is going to be dead plus live plus seismic. Again, the factor is 1, 0.8 and 0.8. Earthquake has 4 different containers, so 4 cases for this. 1 container with plus and 1 with minus, so 8 more cases. So when it comes to serviceability, we have these many criteria. For the dead and live, we have 1 case. Dead plus wind, we have 8 cases. Dead plus seismic 8. Dead live and wind 8. Dead live and seismic 8. So at least we should be getting 33 cases, considering the fact that we have taken 4 containers for wind and 4 containers for seismic. If you have taken more than that, you'll obviously get more combinations than this. So this is all about the serviceability criteria. Let's move on to the proportioning. Now, when it comes to proportioning, this is basically dependent upon just the substructure, that is just the foundation. So we'll be talking about only proportioning with respect to foundation. Just remember, however, that for foundation as well as for the columns, we'll be considering reduced live loads. So the combinations kind of remain the same, but internally the load types will be a bit different. So let's take them together and talk about it. Now, when it comes to the foundations, or rather the proportioning for the foundation, this comes from the clause of IS 1904, which talks about the proportioning of foundation. So you can see it clearly says that the foundations shall be proportioned for, that is, the area defining shall be done with respect to the following load combinations. So right here you can see we have the dead load and imposed load case, and we have the dead load, imposed, and wind load case. Right here we do not have a simple case called dead load plus wind load or dead load plus seismic load, as we have seen inside IS 456. So we are working with different cases now, and we'll go through them one by one. A quick side note, if you are liking this video so far, please do not forget to hit that like button. It really helps. So let's go through this criteria very quickly. We'll start off with the dead load and imposed load case. So the dead load and imposed load or the live load case is very simple. So since there is no factor mentioned, this is basically talking about a single factor. So we are taking 1.0 dead load plus 1.0 live load. So this is one case. Next up, we have the dead load plus imposed plus wind load or seismic. We'll first talk about dead plus live plus wind. You can see we have a factor of 1, 1, and 1 instead of 1, 0.8, and 0.8 as was given in the serviceability criteria inside IS 456. So this is simply 1.0 dead plus 1.0 live plus 1.0 wind load. Again, just to reiterate, this factor is given as 0.8 and this factor is given as 0.8 inside IS 456, table 18. So we are not working with that now. We are working with this criteria where we have 1, 1, and 1 with respect to right here dead plus imposed plus wind from IS 1904. Just like before, we have 4 different containers for wind. So we'll get 4 different cases. Again, we'll get 4 additional cases with a negative sign for wind. So we get 8 cases for dead plus live plus wind. The same will go for dead plus live plus seismic again. Everything remains the same. Just the fact that wind load is now replaced by earthquake. Again, we have 4 containers for earthquake. So we get 4 cases. And then we get 4 additional cases with a negative sign. So we get 8 cases in total. All in all, when it comes to proportioning of foundations, we get these 3 load combination types. We get dead plus live, we get 1 case for that. Dead plus live plus wind, we get 8 cases for that. And dead plus live plus seismic, we get 8 cases for that. All in all, a total of 17 load combination cases. Let's sum it up. For the ultimate strength or the limit state of collapse, we will work with the superstructure as well as the substructure. So we'll be working with beams, slabs, and columns. However, just remember that for columns, the load combinations will remain the same, but the internal load for the live load will be replaced with a reduced live load. So you should always remember that. The same goes for foundation. The combination types will remain the same, but when we are talking about the live load part, which comes into picture, that live load will have to be reduced for columns. So all in all, for the ultimate strength, we got 49 cases. For the serviceability, we were working just with the superstructure, that is the beams, columns, and slabs. We got 33 cases. And finally, for the proportioning part, just for the foundations, we got 17 cases. So whenever working with load combinations, always keep in mind these three concepts: the load types, the member types, and the combination types. And I've shown you quite in detail as to what each of these types means when it comes to the combination or load combinations. So that was all about load combinations. Again, remember the load types, the member types, and the combination types, and how they are interlinked together. Also, do not forget to understand the concept of reduced live load, which although seems to be a very small thing, that is something which is often overlooked by structural designers. So I really hope that this video made sense to you. If it did, please do not forget to hit that like button. It really helps me going with these videos. And one more request, if you are someone who works with different codes as well, please reach out to me in the comments so that we can kind of work on a comparative study of the load combination with respect to, say, the Indian Standard Code and the American Code and the British Code. So if you're working with any of the international codes, please reach out to me because I cannot go through all the codes. I'll be really needing your help to understand what are the comparisons with respect to the different factors which we have seen with respect to different national codes. So I hope that you'll help me out in that endeavor. That's it from this video. I hope you really liked it. I really had a good time making it. Thank you for watching, and I'll see you on the next one.